Hi viewers, we will continue our class on radiation heat transfer. Emissivity is the ratio of the emissive power of a real surface to the emissive power of a black surface which are maintained at same temperature. So that is important. Both the bodies should be at the same temperature. There are two bodies, both are at same temperature. One is a real body and the other one is a black body. And if the temperatures are same, the emissive power of a real surface or real body to the emissive power of a black surface is known as emissivity. And as you know, black body is a perfect emitter and it will emit maximum radiations. So emissive power of a black body is maximum compared to the emissive power of a real surface. You have to compare at same temperature. If it is at different temperature, the emissive power of a real surface may be more, which is at a higher temperature than a black surface. Emissive power of a real surface can be more. But when both the bodies are at same temperature, the emissive power of a real surface is always less than the emissive power of a black surface, because black surface is a perfect emitter. So emissivity of a real surface always less than unity. Generally, emissivity refers to the total hemispherical emissivity. Total hemispherical emissivity. That means you are taking emissive power of a body in all directions, considering all wavelengths. That is total hemispherical emissivity. And generally, emissivity refers to total hemispherical emissivity. We will see what is a spectral emissivity. Spectral emissivity means the ratio of monochromatic emissive power of a real surface to the monochromatic emissive power of a black surface when they are at same temperature. When both the bodies are at same temperature at a particular wavelength, monochromatic emissive power of a real surface and monochromatic emissive power of a black body, then the ratio is known as spectral emissivity. So you consider two surfaces which are at same temperature. One is a real surface, other one is a black surface. Both are at same temperature. Then monochromatic emissive power of this real surface to the monochromatic emissive power of a black surface is known as spectral emissivity. So spectral emissivity is a ratio of monochromatic emissive power of a real surface to the monochromatic emissive power of a black surface which are maintained at same temperature. So that is important. Both the bodies should be at same temperature. At a given temperature and wavelength, monochromatic emissive power of a black surface is always maximum. So spectral emissivity of a real surface is always less than 1. Directional emissivity. So this is a ratio of emissive power of a body in a particular direction to the emissive power of a black body in the same direction. So you are taking a specified direction, and in that direction, what is the radiation leaving per unit area per unit time of a real surface to the radiation leaving total radiation leaving in the same direction for a black body. That you are comparing, and that will give the directional emissivity. So directional emissivity is the total emissive power of a real surface in a specified direction to the total emissive power of a black surface in the same direction when they are at same temperature. When both the bodies are at same temperature, you should compare. Since the black body will emit in any particular direction, if you take, black surface will emit maximum radiation. Directional emissivity of a real surface is always less than 1. Kirchoff's law. It states that the ratio of total emissive power to the absorptivity of a body is a constant for all bodies which are in thermal equilibrium. Now consider 4 different surfaces which are in thermal equilibrium. Thermal equilibrium means there is no net heat flow into the bodies. So it is these 4 bodies are in thermal equilibrium with its surroundings. Now emissive power of this surface 1 is E1. Emissive power of this surface is E2. And similarly, you have E3 and EB. EB, this is a black surface, so emissive power is EB. And EB, you know, it is maximum. Since all are in thermal equilibrium, they are at same temperature, so EB is going to be a maximum. Now, Kirchoff's law states that the ratio of emissive power, that is total hemispherical emissive power, E1, to absorptivity, alpha 1. That absorptivity of that fraction of radiations absorbed by the surface, that is absorptivity. So the ratio total emissive power to absorptivity is a constant for all bodies which are in thermal equilibrium. That means E1 by alpha 1 is equal to E2 by alpha 2 is equal to E3 by alpha 3 is equal to EB by alpha B. Now alpha B, we know it is a absorptivity of a black surface and it is equal to 1. So that equation I have written here, E1 by alpha 1 is equal to E2 by alpha 2 is equal to E3 by alpha 3 is equal to EB by 1. So Kirchoff's law states that when bodies are in thermal equilibrium with its surrounding, the ratio of total emissive power to absorptivity is a constant for all bodies which are in thermal equilibrium with its surrounding. So now taking the first term and last term, we can rearrange this E1 by EB. We are bringing the EB to the left hand side. So E1 by EB is equal to alpha 1 by 1. So E1 by EB is alpha 1. Alpha 1 by 1. So alpha 1. Similarly, taking the second term and the last term, bringing EB down, E2 by EB is equal to alpha 2 by 1, which is alpha 2. So E2 by EB is alpha 2. Now E3 by alpha 3 is equal to EB by 1. I am bringing EB to the left hand side. E3 by EB is equal to alpha 3 by 1 or alpha 3. So E3 by EB is alpha 3. Now we know E1 by EB, the term is familiar for us. So E1 is the emissive power of a surface 1. So the E1 is the emissive power of surface 1 to the emissive power of a black surface. Since all are in thermal equilibrium, they are at same temperature. So you are comparing the emissive power of a surface 1 to the emissive power of a black surface at same temperature. And we know that it is emissivity. So we know that the ratio is emissivity. And this is a ratio of total emissive power of a surface, that is a surface 1, to the total emissive power of a black surface at same temperature, which are in thermal equilibrium, so at same temperature. So E1 by EB is epsilon 1, that is emissivity of surface 1. Similarly, E2 by EB is total emissive power of surface 2 to the total emissive power of a black surface. Since both are at same temperature, this ratio you can take it as emissivity of the surface 2, that is epsilon 2, and that is equal to alpha 2, and similarly this is epsilon 3 is equal to alpha 3. So that what we are getting is epsilon 1, that is emissivity of surface 1 is equal to absorptivity of surface 1. Similarly, epsilon 2 is equal to alpha 2, epsilon 3 is equal to alpha 3. So this means the emissivity and absorptivity of bodies are equal. When they are in thermal equilibrium with its surrounding, their emissivities are equal to absorptivity. Emissivity and absorptivities are equal when they are in thermal equilibrium with its surrounding, and this is known as Kirchoff's identity. And it shows when bodies are in thermal equilibrium, absorptivity is equal to emissivity. Now we'll see what is a gray body. A gray body is one which the emissivity and absorptivity does not vary with the wavelength of the emitted radiations. Then the body is known as gray body. So usually real surfaces, the emissivity and absorptivity will vary with the temperature and wavelength of the emitted radiation. Small variation of emissivity occurs when the temperature and wavelength of the emitted radiations change. So it is depending on the temperature and wavelength of the emitted radiation. So emissivity, as you know, it is a ratio of emissive power of a body to the emissive power of a black body, which are maintained at same temperature. So this will vary with slightly, that ratio is not a constant. It sometimes vary with the temperature and also depending on the wavelength at which the radiations are emitted. Small variation of emissivity and absorptivity takes place. Now, gray body assumption neglects this variation. We assume that these variations are negligible and we treat the emissivity and absorptivity as constant. So that is a gray body assumption, and I will explain this with the help of a diagram. This plot shows the monochromatic emissive power with the wavelength of emitted radiation for three different types of surfaces: black surface, real surface, and gray surface. For a black surface, we know this is for one particular temperature, at any particular temperature, say 1000 Kelvin. So the monochromatic emissive power is varying with the wavelength. This is at a one particular temperature, say 1000 Kelvin. So it is varying with the wavelength. And the wavelength increases. Initially it is increasing, then later is decreasing. It tends to 0 later for infinite value of lambda. Now, any particular wavelength you take, the monochromatic emissive power of a black body is greater than that for a real surface. A real surface is this. It is changing, fluctuating like this. Monochromatic emissive power is more here, and then suddenly it decreases, increases, decreases. So there is a fluctuation for monochromatic emissive power of a real surface with the lambda. It suddenly changes. Okay. This is for a gray body. That is, we are neglecting the fluctuation and taking it is not fluctuating so much, and that is a gray body assumption. Now, what is the emissivity? The ratio of emissive power of a real surface. Suppose you take this point, that is this particular wavelength you take, say lambda 1. If you take this monochromatic emissive power of a real surface, so that is you get the value here, and again at the same wavelength monochromatic emissive power of a black body, you will get that ratio. That ratio is very close to 1 because this is nearly equal to that of black body. It is almost the curves are very close. So this ratio is tends to 1. But if you take another wavelength here, say lambda 2, corresponding value of for your black surface, the emissive power you get here, and for a real surface it is less. Now the ratio is different here. Ratio is almost 50%. So it has changed totally. Like this was more, the emissivity was nearly 1, and this is near to 0.5. So much variation will not take place. But as an example, I explained this. So there is a variation of for a real surface from one wavelength to another wavelength. So emissivity is changing. So the variation is there for emissivity from one wavelength to another wavelength. But as a gray body concept, we are neglecting the variation. This variation will not be so much. So much variation for emissivity will not take place with the wavelength of the emitted radiation. So we are neglecting that variation and taking the average value of this monochromatic emissive power, and we assume that these variations are negligible. Suppose you take this particular lambda value, this ratio, emissive power of a gray body to the emissive power of a black body, you get somewhere around 0.5, say 0.5, and you take another lambda value here. So this value to this corresponding value, again it's 0.5. So take another value, okay, another lambda value. So the ratio always remains same. Both are increasing. So suppose this peak, if you take this value corresponding to this lambda, so the peak, so you are getting the same ratio. So that it's the gap is increasing, but that doesn't mean that ratio is not constant. Both values are increasing. The ratio remains constant. So we assume that ratio remains constant, but there is no fluctuation for, as such, a real body there will be a fluctuation for this ratio. But gray body concept is we are neglecting the fluctuations in that ratio and assume that is constant. We assume that emissivity is constant with the emitted radiation. That is a gray body concept. Now I will show another plot here. So emissivity for a black body, emissivity is 1 because emissivity and absorptivity is equal to 1. Okay, so it is maximum and it is equal to 1 because emissivity means emissive power of a real surface to black surface. It's the same temperature. So the black body means, so both the numerator and denominator are same. So you get emissivity as 1 for a black body. So this is emissivity of a black body, and it also does not change with the wavelength. Any wavelength you take, it will have same emissivity. It is emitting the same radiations. So there is no change in emissivity with the wavelength for a black body. Now for a real surface, it's actually fluctuating. Emissivity is changing because we have seen that ratio is different at different points. So when you take different lambda values, that values are fluctuating for a real surface. So this plot for a real surface, it is fluctuating. For a gray surface, the ratio, you take the ratio here and the ratio another point, that will remain same. So that is a gray body concept. So we are neglecting this variation. We are taking the mean value or average value and assuming that emissivity is not changing with respect to lambda of the emitted radiation or wavelength of the emitted radiation. That is a gray body concept. Lambert's cosine law. Now it states that the total emissive power in a given direction. Emissive power in a given direction. It states that the emissive power in a given direction is proportional to the cosine of the angle of emission. This is radiation emitted per unit area of the surface per unit time in this particular direction at an angle theta from the normal to the surface. So this is a emissive power in that given direction. The total radiation emitted in that direction is represented by E theta. That is the total radiation energy emitted per unit time per unit area of the surface. So that total emission is proportional to the cosine of angle of emission. That is Lambert's cosine law. So that means E theta is proportional to cos theta, and proportionally constant is k. So E theta is equal to k cos theta. You get proportionally constant k. When theta is 0, if theta is 0 means normal to the surface in this direction, normal direction. When theta is 0, if you substitute theta 0, you will get cos 0 is 1. So you will get it's equal to k. Cos 0 is 1, so En is equal to, we will represent that emissive power in the normal direction as En. Okay, so En is equal to k, or substituting this k value we get as En. So substituting k as En, we will get E theta as En into cos theta. So that means the emission in a given direction, the radiation energy emitted in a given direction per unit time per unit area, now it's equal to the radiation energy emitted in the normal direction into cos of the angle of emission. So in this direction you will have a radiation emitted. To calculate the radiation emitted in a given direction, if you know the radiation emitted in the normal direction, you multiply with the cos theta. That will give the radiation emitted in a given direction. So radiation emitted in a given direction is equal to the radiation emitted normal to the surface into cosine of the angle of emission. Thank you for watching.